Okay, in section 7a, we're going to talk about fundamentals of probability. Essentially, we'll introduce some basic definitions that we're going to need, and we'll calculate some very basic probabilities. So the first thing we need to know in any probability experiment, so this is maybe flipping a coin once or flipping a coin 2 times or tossing 2 coins at once, anything that we might observe that has chance in it, we'll consider as a probability experiment. So in a probability experiment, our most basic element is an outcome. So this is, in the case of tossing 2 coins, perhaps, that's the probability experiment. One outcome is heads on the first toss, tails on the second toss. Another outcome, tails on the first toss, heads on the second toss. So it's any possibility, any arrangement of heads or tails that we can have for 2 coin tosses. Now, the next thing we have is an event. So, an event consists of one or more, or maybe no outcomes, possibly even. So, this would be a collection of outcomes. It could be just a single outcome, and it might have no outcomes in it. So, tossing 2 coins, one event could be landing 1 heads in the 2 tosses. So, that would look like this: heads, tails, and tails, heads. This is an event in which one heads or 1 tails has occurred. So actually the event here is event of 1 head. So this is 1 heads here and 1 heads here. So there are 2 different outcomes in the event of landing 1 heads on a toss of 2 coins. So the last thing we'll consider, the last definition we have from this page, is the sample space. This is the set of all possible outcomes of a probability experiment. So to put all this together, let's go below here and write this up. So we're going to toss a coin 2 times, or toss 2 coins, it's the same thing, with heads or tails on either face. So let's list all our possible outcomes. So we have heads, heads, we have heads, tails, we have tails, heads, we have tails, tails. It's a very natural thing to do. If we can write down every outcome that would occur in this probability experiment, then we might do so. It might make our calculations easy. As a whole, this is our sample space. It's defined above. It's the set of all outcomes for this probability experiment. And each one of these elements inside the sample space is an outcome. Okay? Lastly, the event of 1 heads, exactly 1 heads, if it doesn't say something like at least 1 heads or anything else, if it just says the event of 1 heads, well, we're going to count up only the events that have exactly 1 heads landing in them. So here's 1 heads here, 1 heads here. These 2 outcomes, here and here, make up an event. And that event is 1 heads. Say it like that. Okay? So we all see how this leads into discussions of probability of an event happening. So what we might ask is, what's the probability of 1 heads occurring? Right? Just to use some new notation, P, the probability of the event 1 heads occurring. That's at least a decent shorthand for writing it. Well, I think most of us can look at this and say, okay, there are 2 outcomes, 2 ways in which 1 heads can occur in 2 tosses, out of 4 total ways that this outcome, or this experiment can come out. So we know that our probability of 1 heads occurring is 2 out of 4, and of course that reduces to 1/2. Okay, so we see how this leads into probability. Let's give a more clear definition for what probability actually is. So, theoretical probability, we look at an event E, and N of E is the number of outcomes contained in that event. So we've seen those definitions, we know what that means. For a sample space S that E lives within in terms of the probability experiment, well, if we want to calculate the probability of E, P of E, it's the number of outcomes in the event E divided by the total number of possible outcomes. That's exactly what we just calculated. Here's some more notation. The number of events in E divided by the number of events in the sample space S, if we want either of those. So Let's have a look at the example below to make these things a little bit more clear. One thing we'll note before we get started is that probability is a number between 0 and 1. It's never below 0, it's never above 1. Think of it as 0% to 100%. And an event with probability 0 means that it's impossible. It can't happen in our experiment. And an event with a probability of 1 means that the event is certain. It means it will absolutely happen. So let's have a look at what we've got below in the example with those things in mind. So find the probability. We're going to toss a coin twice. I'm going to calculate the probability of first heads, then tails. Okay? So the probability of heads, then tails. This is the event that they're describing. Put it in set notation to make it look like an event or a collection of outcomes. Well, when we remember our sample space, let's draw that off to the side here just so we have it again. We have heads, 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 tails, tails, heads, tails, tails. Remember that, well, there's only one event or one outcome in the event heads, then tails. There are 4 outcomes total. So using the formula from above, we can write that the probability of heads, then tails is 1 way to get heads, then tails on 2 tosses, divided by the 4 outcomes that are actually in this experiment. Okay? Now the probability of heads, heads is very similar. So the probability of heads, heads as an event, well again, that's just a single outcome in our probability space. We look over here to the right. The only thing that satisfies this is this single outcome. So that's the only outcome in our event of heads, heads. And that's divided by the 4 possible outcomes of the space. And again, we end up with 1/4. Now let's see. Number 3 down here says the probability of the same outcome on each toss. So a couple of different ways we could write this. I think the easiest is just to say, okay, the probability let's just list the outcomes that fulfill this event. Heads, heads, that's the same outcome on each toss. Tails, tails, that's the same outcome on each toss. What's the probability of getting heads, heads, or tails, tails? Well, we look up. So here's heads, heads, here's tails, tails. Each of those outcomes occur once in the total 4 outcomes. So that's going to be 2 out of 4. 2 ways for this to happen, to have matching tosses divided by the 4 total outcomes. So 2 outcomes divided by 4 outcomes. Now, tails on the second toss. Okay, that is, we don't really care what happens on this toss, but this one needs to be a tails. It's one way to look at this as a set of outcomes. And we'll go back over to our table. And tails on the second toss. Here's where we have tails on the second toss. And this one we have tails on the second toss. Again, it's 2 out of 4. This is 2 out of 4. Notice in the above problem we didn't simplify to 1/2, though we could. The problem didn't ask us to, so this answer was just fine actually. But we'll simplify when we can just because it's nicer to do so. Now, let's see, the last one. At least 1 head in 3 tosses, or 2 tosses. Probability of at least 1 heads. Okay, well we can count that up again from our table. Just to change colors a little bit. Here's at least 1 heads. 2 is fine because that meets the criteria of at least 1. Here's a heads. Here's a heads. 3 of those pink or purple highlighted outcomes versus 4 total. So we have 3/4 probability. 3 ways for at least 1 heads out of the 4 total outcomes. So there's our basic probability calculation for tossing a coin 2 times and many different events that can result from that and many different ways we can cut this problem. So let's move on to see the multiplication principle. And this allows us to count up the number of outcomes that will be in a sample space. That's really useful because if you think about whether or not we know when to stop if we're counting up something like this, well, if we're tossing a coin twice, it's pretty easy to list them all. If we toss a coin 4 or 5 times, it's going to be a little bit more difficult to understand how many of these things should be here and whether or not we've got a complete list if we're going to try to write out the sample space. We won't always try to write out the sample space, and that'll make this rule over here even more useful. So the multiplication principle, this is a method of counting things. We're going to be able to count up the sample space, maybe even sometimes count the number of outcomes in an event with this tool. So I'm just going to skip right into the example, and we'll come back and look at the rule when we're done. So a restaurant offers 8 appetizers, 9 main courses, 2 desserts. And how many ways can a person order a 3-course meal? In other words, how many combinations of appetizer, main course, and desserts are possible? Well, it's a pretty straightforward calculation. Let's represent each course with a line here, a dash. Okay, so our appetizers here, maybe our main course we'll put in the middle, and dessert put on the end. Okay, how many choices do we have for an appetizer? Well, 8 according to the problem. And then how many choices for a main course? 9. How many choices for desserts? 2. Well, how do we combine these things? Well, the rule above says multiply these things. Okay, however many different courses or different stages we have, we multiply the number of choices or possibilities in each stage times the number of choices or possibilities in the next stage. And that's exactly what we'll do right here. So 8 times 9 times 2, and this comes out to 144 combinations or 3-course meals in this situation. So it's a very straightforward counting rule. It's the only one we'll have in the class, and it'll cover most of the things we need it for. Now, another question. How many possible outcomes are there for the experiment of tossing a coin 3 times? Okay, well, we're going to toss a coin 3 times. Let's set it up the same way. First toss, second toss, third toss. So first, second, third. Okay, well, this way, we were not told how many possibilities there are in each coin toss, but if we think about it, we'll get it. On the first toss, we have heads or tails, so that's 2 possibilities on the first toss. Well, in the second toss, it's just the same. Either heads or tails comes up on the second toss. Third toss, heads or tails occurs, so 2 possibilities there. What do we do with all these? Multiply them. We have 8 total outcomes in this situation. That's really useful because if we wanted to write down that sample space or calculate the probability, we need to know this number. We need to know how many possibilities there are and or how many outcomes there are for tossing a coin 3 times. Now, here's another question. How about 4 tosses? Just to add to this problem. Well, I think we can all see pretty quickly, times 2 again is going to give us 16, but to lay it all out, 4 tosses now, 4 dashes, 2 possibilities in all 4 of these, times, and we end up with 16 outcomes. And I think we could start to see a general rule here that if we have 4 tosses, then and 2 possibilities on every toss, we can just write this notation as 2 to the 4th equals 16 outcomes. So maybe a shortcut. So if we have 10 tosses, we would just calculate 2 to the 10th, and that would shorten our work instead of having to write out 2 10 times. So this exponential notation is pretty handy here. But either way you get to it, that's just fine in this problem. Now let's move on to another type of probability within this theoretical probability, and that's complementary probability. So sometimes it's more convenient to calculate the probability of an event not happening versus the probability of it happening, or vice versa. So in this case, we might look at this and say we want to know what the probability that E does not occur. So if we already know what the probability of E is, we can get it through this overall formula that we're looking at right here. This whole thing will tell us one given the other one. Where does this come from, we might ask? It's the following. We have an event E. So if we think about an event occurring, maybe we'll call this, it's going to rain on campus today. It's the probability E, the probability that it will rain on campus today, plus its complement is its opposite, not E. So that would be, it does not rain on campus today. Okay, probability of not E. Well, let's think about this in a reasonable way. It either happens, either it rains on campus today, or it does not rain on campus today. Those two things combined, one or the other, is going to happen in absolute certainty, right? So this is a 1. That means that adding the probabilities of these events together, we should make up the entire realm of possibility. E happens or it doesn't happen. It rains or it doesn't rain. We know that with 100% certainty. Okay, so if we want to build the formula down here, we just think about this situation, and it informs us. If we subtract probability of E from both sides, we'll have this formula given right here. Okay, so that's where this comes from. If you want to remember that, that's nice. If not, we can just use the formula as is. So we have a very similar one. We can build this formula in a similar way, except this time we subtract the probability of not E from both sides, and we arrive at that equation. So let's look at the example. We roll one 6-sided die. Find the probability that you don't roll a 4. Find the probability that we get not a 4. So this will look like probability of not 4. Okay. Well, we know a quick rule. If it's probability of not something, we can say 1 minus the probability that it does happen, the probability that we do roll a 4. I've just used this formula right here to reverse the problem. Now, I know it might be easy in this problem to just write out the sample space for a 6-sided die, numbered 1 through 6, and say, okay, add up all the outcomes that aren't 4, divide by the total number of outcomes, and there we go. But just to demonstrate this rule, which we'll use later, this is a nice problem still. So remember that rolling a 6-sided die, or note that we have 1, 2, 3, 4, 5, or 6 that will show up on a 6-sided die. When we mention a 6-sided die, we just mean simply numbered 1 through 6. Fair, it's got an equal probability of landing on any one of these faces and showing those numbers. So the probability of rolling a 4, well, there's only one 4 on this list out of the 6 total outcomes. So that probability of rolling a 4 is 1 out of 6. This is 1 minus 1/6. Okay, we've got a whole number minus a fraction. We'll multiply 6 over 6 times 1 to give us a common denominator with this 6 right here. So 6 over 6 because we saw this 6 right here in that denominator. And this will leave us with 6 over 6 minus 1 over 6. Once they have common denominators, we can combine the numerators as follows. And we have 5 over 6. And that's our probability. The probability of not rolling a 4 is 5 over 6. So perhaps this example isn't the best to show why it's useful to have this formula around, but it does demonstrate that it's accurate, because we can all look at this and say there are 1, 2, 3, 4, 5 ways to not roll a 4 out of 6 total possible ways, and that matches our answer right here. So that's the complement rule for probabilities. Let's move on to forming a probability distribution. We'll see this in the next video for 7A Part 2.